Morning, everyone. So, can you see my screen? Okay, fine. Okay, so let's start today's class. Uh, Before I start, just to give you a quick overview of what we did last time. Last time we started with finding what's a computational problem, what type of problem we are going to solve in this course. And one particular example that we started with was of the sorting problem. Right? I just placed this sorting problem in a slightly different way than you have seen before. Like this time, instead of saying just numbers, I'm saying I'll take few objects from a well-ordered set, and then I can arrange them. So, its voice is low. Is it? Okay, just let me. Hello. Hello. Can you hear me properly now? Okay, fine. So I'll use this mic only. Okay. So we have seen this problem, the sorting problem, and with the help of the sorting problem, we defined what's an algorithm. It's just a well-defined rules to solve some computational problem. And then we looked into this particular example of an algorithm that sorts some numbers. Here I have taken, for example, some numbers. And we discussed this insertion sort last time. Okay. We have taken one example and have seen how it works. And then I wrote the pseudocode. Okay. And then we talked about the correctness of this process. Using mathematical induction, we can actually say that this process is correct. And then we started analyzing the efficiency of this algorithm, efficiency of this insertion. Right. So what we did was we said that we just not write the code for an algorithm and then check the clock time. System just measure the system clock. That's not the way to measure an efficiency of an algorithm. But instead, what we do, we will count the primitive operations that we are performing inside the cell. Okay. And then we started calculating the primitive operations for this algorithm of insertion set, right? And I asked you to come up with an expression of the number of primitive operations that we have done in this. Right? Last question that was I tried, but okay. So it's a So the question that I have given is count the number of primitive operations. Right? And in fact, I have discussed this in here. So for first line, it takes n operation, like not just n, but actually it's some multiple of n. Why am I saying so? If you see, like inside this, so think about this line for I equal to 1 to n minus 1. And just recall from your programming course how this for loop works. Right, first is it takes I equal to 1, and then it compares the termination condition, whether this I, current I, is less than n minus 1 or not. And if it's yes, then it does something, it goes inside the loop and does something, and then after that, its I is getting incremented. So there are mainly three things happening here. So one assignment, I take some value, 1, 2, 3, 4. That's an assignment part. Then we have a checking whether I is less than n minus 1 or not. And then also I has to be incremented by 1. Right? So there are few things happening, but I'm saying why I'm saying it's n is because uh, it's some constant multiple of n. To be precise, I should be writing something like not just n. It should be, to be accurate, it should be some constant times n. Should be something like this. Right? And that is true for all the other things also, like line 2, line 3, for everything that's the same. Right? So what I asked you to do is just come up with this expression of total primitive operations that we are doing inside this thing. So what do you have to do? Some C1 times n for this first line, some C1 times n plus some C2 times n minus 1, then C3 times n minus 1 again. Like this I want to. So if I do that, let me write the expression. Say, let's say I define this Tn to be the number of primitive operations done in insertion sort for an input size of n. So when you have please explain. Okay, so when we have an array of size n, in terms of n, we are actually calculating this. Okay, so what's happening in line 4 is something different than the other previous lines. It's like what I said here. So I need to check I need to know how many times this checking in the for loop is in the while loop at line 4 is being done. Right. The point is it's not fixed for all the values of j. Uh, for all the values of I. It depends on the value of temp itself and all the previous numbers that we have. For example, we have seen this case. When we are trying to insert this number 21, So what was the status? Like some part was unsorted and some was sorted. For example, this part at this point, this part was sorted and this is unsorted. Now I'm trying to insert this 15. Right? So now how many times do I have to check? I have to check with this one and I have to check with this one. Right? Only two checking I have to do. But rather compare it with the last thing. So when I'm trying to insert this 8, so I have to do this checking with this one, this one, this one, this one, and also with this one. Then I come to know that its correct position is somewhere in between. Right? So that's what I said, that the number of this checking, number of times this while loop conditions will be checked is not fixed for different values of I. That's why uh, I have said that let Ti be the number of times while loop conditions are checked. Okay. I hope this is clear now. And total time for this while loop is sum over all I Ti. Right? That's what we. So now if I write the total expression for this, what does this look like? So as I said, so for line 1, it will be some constant times n. For line 2, it will be some constant times n. I'm taking different constant because the other things that we are doing, so it should be n minus 1. The other things that I'm doing is not always same. For line 4, what's happening is again, so some constant times, all the works that I have done, 1 to n minus 1. Yes. And same for the next line. I runs from 1 to n minus 1. What was this? This was Ti minus 1. Yeah. For sixth line, we have the same expression. So 6. Sum for I runs from 1 to n minus 1. Pi minus 1. And for the last line, it's just an n minus 1. Yes. C7 is n minus 1. Right, so we have a very complicated looking expression here. Right? So, so this for to understand the efficiency of this algorithm, uh, I said that we have to count the total number of primitive operations. And in fact, it turns out to be something of this type. So we need to do. So I have uploaded these slides, not slides, it's lecture notes, right? So you can check it from there. And I'll tell you what to do in the tutorial class and also in the lab. But for the time being, you just focus on what I'm saying. So this is the a complicated looking expression that we have ended up with. So what to do in this case? So this expression doesn't give me a clear picture how good or how fast this uh, insertion sort is. So now we are going to simplify this expression. So what we should be doing here is first thing we'll do the worst case analysis. Worst case. What do I mean by this? So I will take, so if you think carefully that different values of Ti will give you different type of expression. So for example, can you tell me what if this Ti is 1 for all I? For every value of I, Ti is 1. Then can you tell me what will be this expression in terms of N? Anyone? Okay, let me tell you. So these terms doesn't have Ti, so no need to worry about this. If Ti is 1, then this will become 0. So this term is gone now. If T is 1, this term is also gone now. Uh, yes, it becomes 0, and C4, like this fourth term, will be what? Will be like Ti is 1, and just I'm summing 1 how many times? N minus 1 times. So this will become something like C4 into N minus 1, something like this. Right? So what we can write in this case, my Tn will become something less than some constant times n. Something less than some constant time. Yes, correct. That will have this expression, but oh, I will consider some different constant capital C, and I can say that Tn will be some constant times n at most. At most. Now think about another different situation. This is the case where we have Ti is 1. That means what? What was Ti? Ti is the number of times this while loop will be checked. If you think Ti is 1, that means this while loop is being executed only once. What does that mean in terms of our algorithm? When we're trying to put some element compared, suppose this element and okay. This one. So, okay, this is not a bright example. So I'll tell you here. What does this Pi equal to 1 mean? We have this array. This portion is sorted, and this part is unsorted, right? And this part is unsorted. So now this time I'm trying to insert this element somewhere in the correct place. Right? Now I'm saying Ti is 1. That says that this element here is compared with only the previous element. And then I know I have found its correct place. And this element is not going to be compared with this one. No, that is what Ti is. Like Ti equal to 1. Okay? So why do we have less than? Oh, okay. So less than means, so as someone said, like it will be C1 times N, C1 times N, C2 times N, C3 times, sorry, C2 times N minus 1, C3 times N minus 1, and then C4 times N minus 1, and then these terms are gone. This is C7 times N minus 1. I'm combining all those constants, C1, C2, C3, C4, C7, and taking a bigger constant, and I'm saying that Tn can be at most some constant times n. Right? As I said, I have to express my number of primitive operations in terms of n. This c can be uh, any constant. The point is you can choose a suitable c, capital C. In this case, capital C equal to, I mean, it works for any value more than C1 plus C2 plus C3 plus C4 plus C7. If you add all these things, any value more than that, if you take capital C to be anything more than that, it will work. This statement. Okay. Now, so I hope that you have understood the case when T, what does this Ti equal to 1 mean? Now, what could be the other case? What could be the maximum value of Ti? Think about this. Can anyone tell me what could be the maximum value of Ti? Ti is what? Ti is how many times one particular element has to be compared with its previous element till we find some its correct place. Ti is n minus 1 always for every, do you think for every I, maximum value of Ti will be n minus 1? No. Means. So suppose this is my I. Okay. So how many times this element, at most, how many times this element is going to be compared with its previous elements? Is this element going to be compared with n minus 1 other elements? N by 2 minus 1? No. So this element is going to be compared with these only with its previous elements. How many previous elements do I have? I minus 1. There are how many? This is I. This element is I. So I have I minus 1 elements in here. And this particular element has to be compared with these elements, I minus elements only. Okay. So the maximum value, and for checking condition, I can say that the maximum value that Ti takes is I. Is this okay? No, like so taking example is not a good idea always. So you are doing it's not mm, school level lectures that you're following. So you better take an example and see what's happening. Right? So it will be difficult for me to, at each point I take a concrete example and then work with it. No, it's not that. It doesn't work that way. You have to, now you are mature. Right? So you have already done 1 year of course. So you have to think in this, in general. You have to think in terms of generality, more generality, not always with concrete example. So what I am saying, if this is I, you have to compare this element to all its previous elements. Okay, and uh, how how many, at most how many comparisons that will be doing? I minus one, right? And since you are counting the number of times this conditions of the while loop will be checked, for exiting the while loop, it has to be checked one more time. That's why I have taken at max ti can get the value I. Now, what do you have when you have ti is I? So there's no effect on these terms and also in the last term, right? So these values will get changed. So what will be the fourth term then? So what's the fourth term? C4. It's like fourth term is C4 times summation I. I runs from 1 to n minus 1. What is this term? What will be this value? C4 into what? Summation I, and I runs from 1 to n minus 1. Anyone? So it's not C4 times n minus 1. If Pi was 1, then it was C4 times n minus 1. But yes, it will be something like sum of, yeah, what is it? Like C4 times. So it's like 1 plus 2 plus 3 all the way up to n minus 1, right? So what is the sum? N into n plus 1 by 2. So in this case, this will turn out to be C4 n minus 1 by, like this. Okay, so I hope you get it. So that I can write it as some constant times n square. Can I write this? Yes. So this term, see for this fourth term, I can write it some constant time, let's say d, and write some constant d times n square. Right? And similarly for the fifth term also I can write it some d times n square. This also I can write it some d times n square, and everything else will be independent of ti. So what I'd say in this case, when we have ti equal to 1, then I can write tn is lesser equal to. So the first three terms will be as it is. The fourth term I can write d times n squared, d1, let's say, and d5 times n squared. The fifth term, d6 times n squared. Right? and then C7 and n minus 1 is independent of this. But there is n at half also. I don't know what you have. Explain what? So how is this becoming some constant times lesser equal to some constant times n square? Is it? Uh, does there exist? Question is, does there exist some constant for which you can write this expression? So take your constant, a very big one. Or even like it will work for C4 as well. I can write it at C4 times, like n. Is it that it will have I'm saying it's at most, right? So it's also by 2 is even smaller. N square means n into n. So it's always true, right? So this expression, I can write it some constant terms, constant times n squared, because I have something n or the order n here, but here I have n squared. Right? So in this case, when Ti is I, then Tn becomes some constant times n squared. Right? So the thing is, for different cases, you can have different expressions for Tn. Tn, you can bound it by C times n in some cases. In some other cases, Tn is bounded by C times n squared. Okay. But what do we have to do to analyze the running time of an algorithm is we'll be taking the worst case analysis. So we'll be doing the worst case analysis. That is, we have to take maximum number of operations that the algorithm performs. It's the maximum number of operations that the algorithm performs for all possible inputs. Right? So what is that in this case? So in this case is some constant times n squared. So obviously C times n is smaller than C times n squared. So what we have done here, it's this approximation. So we have a very big expression. So if you think here, uh, we have quite a big expression for Tn, but we have simplified this. How do you simplify this? I am just neglecting the lower order terms. What do you mean by lower order terms? What's the order here? It's a order n. So it's a linear term, linear in n. This is also linear in n. This is also linear in n. This term here, linear in n, right? But these terms are quadratic in n. So these are higher order terms. We will, in the whole expression, will focus on the highest order term, right? And and I also don't care much about the constants here. So when we have multiple it's such a big expression, how to simplify this expression? Right? This simplification step uh, involves that we're going to consider only the high, highest order term. That's what we did here. So we are considering the highest order term, and that also means like neglect the lower order terms and also small constants, right? So that's what, and this will help us in getting the uh, measure of this algorithm, right? So this Tn, will say that the running time of Tn is some constant times n square. Will use this other notation. Some notation is there to express this formally, and that expression is of big O notation that I'm going to define. But for just a simple exercise, you can think. So what? Let me write a piece of code and ask you what would be the number of primitive operations. So, for example, let's say I have two arrays. I am looking for an element, whether an element is there or not. So I have n ones are lower order. Why having n? Um, why having n? Those terms are lower order. Lower order means what? Lower order means like it's a this term is linear and this term is quadratic. So which one is of higher order? Quadratics are the higher order. Is this okay? Suppose I have two arrays, let's say array A and B. Both of them are of size n. Right? So I have array A, array B. Both of them are of size n. Right? And I want to find an element T, uh, whether it's there or not. Let's say I write this. So if AI is equal to T, then return. And so this element is there in the array. And for I equal to 1 to n, if bi is equal to t, then again return. Uh, Returning true means like you can think it in a different way of setting some values on, or forget about return true, just to set some variable x is will also exist. So think about this piece of algorithm here, right? How many primitive operations are we doing in this? Can anyone tell me how many primitive operations are we doing? Yes, is it how many? My question is how many primitive operations are we doing in this? So again, I'll do. You can do it in a similar way. Right. So in the first line, it's like c times n. So I varies from 1 to n, and for each of these I, we are checking for each of these uh, I, you are checking whether AI is equal to T or not. Right? So that is one checking for each I. So this will be again C times some constant, let's say C1, C2, another constant I take. And if that is yes, then X is equal to 1. Okay. And this will be like how many times this X equal to 1 will be executed? Can you tell me how many times this X equal to 1 will be executed? Is it n times? No, it will be executed. X equal to 1 will be executed one time. No, that is also not true. I don't know actually. The answer is I don't know. It will depend on the values of this of the elements of this array A and T. If this element T is not present in this array, then X equal to 1 will never going to be executed. Do you agree on this? And so if it's present, this X will be 1, right? But the number of times this X equal to 1 will be executed is basically the number of times T is appearing in the array A, right? That is not always n minus 1, or that is not always n or 1. Okay, it's the answer is I don't know the exact value, but I know that it would be at most some constant times n. That's what I'm saying. We'll be always thinking about the worst case analysis. By the maximum, how many times this x equal to 1 will be executed? That is some constant times n. K times if t occurs k times, correct. But the point is here to analyze, as I said, I'll be taking the worst case always. So I'll be thinking at the maximum how many times this line will be executed. Okay. And same thing will happen for this, some other C4 times n, C5 times n, C6 times n, something like this. Okay. So now can you, so as we're doing Tn. Tn will be at most a very big expression, right? Can you simplify this and say something like Tn will be what? As I did in here. What can you say? Yes, again, we can say it will be some constant times n. Right? Yes, correct. Okay. Let's take one more execution. Yeah, one more piece of code. Let's mm, let me write and then ask you what is this to equal to 1 to n, and inside this for loop I have a j which runs from 1 to n. Sorry, not 1, it's running from I plus 1 to n. And I'm asking if checking if ai is equal to aj, then I'll say then x is equal to 1. Okay, to understand what's happening here, I have an array A and I'm taking two indices I and j, where I is running from 1 to n and j is running from so it's a so you can think of it's 0 to n minus 1, 9 plus 1 to n minus 1. It's also array indices starts with 0. Yes. Now we think how many times these things are being executed. For a fixed value of I, how many times this is being executed? Yes, someone answered it correctly. It will be again some constant times n squared. So if I am somewhere here, I, and what is the range for this j? J is running over all the elements that are beyond I. J is running from I plus 1 to n minus 1, right? So for these cases, so how many times is, and I is from 0 to n. Oh, okay, so the way I did this analysis before, let's do that. So how many times this n will be executed? So I first line again some constant times n, some constant times n. Now how many times this j in inner for loop will be executed? For different values of I, this inner for loop will be executed different number of times. For I equal to 1, this will be executed n minus 1 times. For I equal to 2, it will be executed n minus 2 times, like this. So what should I be writing? It will be some constant times C1, C2, some constant times I runs from 1 to, sorry, 0 to n minus 1. Then, so when I is 0, then what? How many times? So what should I write? I equal to n to 0. When I equal to n, it's 0 times. No, so this summation, what should I write? It's kind of I times, right? Yes. And this will again be something similar to this. Yes, I times, right? So if you do like again, if you do the similar thing, then Tn, you will get something in sum of all I 0 to n minus 1, that will give you something n squared. You'll get something constant times n squared. So please, I'll ask you to complete this. Whatever calculations I have skipped out, please do those things. Those who are not getting it properly. So the point is to analyze this algorithms, you have to check the primitive operations, and you will get a complicated expression, and then you simplify it. How to simplify this? Just focus on the highest order term and throw away all the lower order terms. Right? And why we are doing it, that comes for our why, because we will try to express our running time in terms of some notation that we'll introduce now. So it's called big O notation. So I'll first define what it is. Like it's a Tn, some uh, function is big O of Fn if and only if Tn is eventually bounded by bounded above, bounded above by uh, constant multiple of Fn. What do I mean by this? So this is the idea of big O notation. What do I mean by this is something like this. So if I draw the graph, then I think it will be good. Maybe your Tn is something like this. This is your Tn. And you have some, this is the graph for constant times Fn. What do I mean by this? So in this x-axis, I have the values of n, and in this y-axis, I have the function values of constant times Fn and Tn. Bounded above means that Tn will be lesser equal to some constant times, right? So Tn is bounded above by a constant multiple of this. Right? Now, what do I mean by this word eventually? Eventually means like, see that it's not always that Tn is smaller than uh, C times Fn. Now, for some value of thing in this one. So this value, this is the value of C times Fn. C times Fn is smaller than T of n, right? But see what is happening here. Beyond this point, beyond this point, C times Fn is always more. This is the case. Beyond that point. And that point, I'll say some constant n, some number n, right? So, so this is what it means. Like if I say Tn is big O of Fn, so Tn must be bounded above by Fn eventually. And if I write it mathematically, then I must be saying like this is some n for all n greater than n naught. This is what I mean by eventually. So to write it mathematically, Tn is big O of Fn if and only if there exist positive constants C and N naught such that Tn is lesser equal to C times Fn for all n greater equal to n naught. Okay. This is the meaning of this. For example, the expressions that I had. This I'll say if I have something like this. So I'll say Tn is big O of n. And when I had it's a C times n squared, we'll say T of big O of n squared. Okay. So, so suppose I want you to, this is Tn plus 8. Suppose this. Uh, this will be Tn O of n. Why is that? So to show this, what do you have to do? You have to show the existence of uh, some constant C and N naught such that uh, this definition go through. So if I Tn is Tn is equal to 2n plus 8, so I can write plus n also for and this. Okay, can you tell me, is it can I write this always? Can I write this always? No. Yes, correct. For what values of n this is not true? Yes, for 1, 2, even for 7, right? But the point is for any value more than 8, this is true, right? So this is my n naught. Beyond this point 8, this is true. So this is nothing but 3n. So what do I have here? Tn is lesser equal to some constant times n for all n greater equal to 8. So basically, I am showing the existence of n naught and the existence of the constant. Right? So that's what we have to show. There exists a constant c and n naught for which this is true. Okay, fine. Uh, mm, let's see. Like suppose say Tn is n to the power some k, where k is greater or equal to 1 is a positive integer. Okay. So can I say that Tn is big O of n to the power k minus 1? Is it true? So think in terms of the definition. The definition that I have written in here. This is actually the definition. Uh, why do you think it's true? In fact, this is false. This is not true. Suppose, so we this is, so let's see why this is not the case. So T, by definition, suppose this is true, suppose Tn is big O of n to the power k minus 1. Then by definition, what do I have? There exists some C and N naught such that Tn is lesser equal to some C times n to the power k minus 1, right? So this is by definition for all n greater equal to n naught. So now this will lead me to some contradiction. What is that? So what is Tn? Tn, this actually says that Tn is n to the power k. N to the power k is lesser equal to some constant times n to the power k minus 1 for all n greater equal to n naught. And if you simplify this, n is lesser equal to c for all n greater equal to n naught. Is this statement true? So like your C is has to be somewhere here. So at some point C is a constant independent of this. And but here you're saying all the natural numbers are less than C. It's not possible. So you have all the numbers beyond this. This is the contradiction. Suppose you need to show that some uh, something is not an order of this. Order of, for example, in this case, order of n to the power k, right? This is not the, like, to show how to show this. You start with the definition, and if you do everything correctly, then surely you are going to get some kind of contradiction. So we are going to express our running times in this notation, O of something, O of some. We have seen our running time of insertion sort is O of n square. Now, what would be our goal is our goal is to, whenever we're trying to design an algorithm, our running time should be as less as possible. Our goal is always design an algorithm which is more efficient. In terms of efficiency, if you see, like a linear algorithm will always prefer over a quadratic. Uh, if you have some running time, some algorithm that runs in n to the power some constant, this is called, this is one is polynomial. I will say this is an polynomial time algorithm. This is a quadratic algorithm. This is a linear algorithm. Anything less than that is as a sublinear algorithm. So can you say something what could be a better than n less than n? Some function which is less than n. Oh, constant. Yes. So constant is the best thing that you can have. O of, I'm writing O of 1. It's uh, to represent some constant, right? But if you think carefully, like constant time algorithm means what? You are doing something, just a calculation maybe. So you are adding two numbers as a constant number of operations or multiplying something. Right? Indeed, like if you have a input size of n, as long as your input size is constant, then you can have any kind of algorithm that runs in constant time. Right? But when you have your as a parameter, input size is a parameter, right? Then it's most likely that you will not end up with constant time. Constant means time is not changed with input. Yes. Right. So that's what I am saying. It will not change with input. If your input size is constant, then you can do it in constant time. Okay. So it's something in between could be O of log n. There may be something. So, and do you know any algorithm that works? And so have you done any analysis of this kind? Anything in between n and n square? Anything in between n square can be n log n. So n times log n. Yes, a binary search will give you this log n. And what's beyond it is something exponential, like its running time is 2 to the power n. So some suppose I have Pn is 2 to the power n plus 10. So is it true? Is this true? Yes, in fact, this is true. Like, what is this? This is saying it's 2 to the power 10 times 2 to the power n. And this is nothing but your but a constant. This is exactly some c times, sorry, 2 to the power n. C times 2 to the power n. Right? This is true. Right? Whereas if you take Tn to be 2 to the power 10 into n, then Tn is not this. No, this is not true. You can show it. So if this is the case, suppose this is the case. What does this mean? Tn will be lesser equal to some constant times 2 to the power n for all n greater than some n naught, right? And what is your Tn? Tn is 2 to the power 10 n lesser equal to some constant times for all. So this means what? This is 2 to the power 9n is lesser equal to a constant for all values n greater equal to n naught. Is this true? This is the contradiction, right? This is the contradiction. Okay. So this is not. Okay. So whenever you are confused, just go back to your definition and stick to that. If you do everything correctly, then you'll get some contradiction. So something similar to this, we have another notation and we'll call it big omega. This time, so earlier we had it's bounded above, but this time we'll have it's bounded from below. Right? Tn is big omega of Fn if and only so same thing. So there exists this notation is for there exists. There exists some positive constants C and N naught such that uh, Tn is greater equal to C times N for all n greater equal to N naught. So same thing. Earlier we had this Tn is lesser equal to some constant times Fn. This time is Tn is bounded from below, greater equal to some constant times. Uh, so for example, if I take the same thing, like Tn is n to the power k. Earlier we said that Tn is not big O of n to the power k minus 1. But Tn, in fact, omega of n to the power k minus 1. This is like, I have to figure out some function which is significantly for all values of n beyond certain point, it's significantly less than Tn. Right? But I cannot say that Tn is last point. GP means not. Oh, okay. So this one you didn't get. Okay. So let's see. So can I find some constant? What does this mean? And n to the power k is greater equal to some constant times n to the power k minus 1. Does there exist some constant which satisfy this? Yes, obviously. Uh, I can take C to be 1 and N to be anything more than 1 for this. This will true. Sorry, not N not. N is greater than N not. N not is N not is 1. Yes. Why do we need big omega notation? That's an interesting question. Uh, So what we say that like for an algorithm, when I analyze the algorithm, we measure the worst case thing and say that this is the worst case, and I my algorithm runs in at most n square time, like constant times n square, or at most constant times n log n time, something like that. But when I say that some function, maybe Tn represents some running time of an algorithm whose input size is n, then uh, then what does this omega mean? Like some running time Tn is omega of n, let's say, right? It's not okay. Someone said it's the best case, but it's not always the best case. It's a I mean, in the best case, okay, so you can say it's a best case, but you need to understand this properly. That best case means what? You have a specific input eh, for which, let's say you can get the correct answer after n many primitive operations. But here it says that if you want to solve that particular problem, you must be doing some constant multiple of n many operations. We must have to perform this at least at least this operations. Okay. It's not always the best case, but it says that to solve this problem, I must be doing at least these many operations, and then I'll be able to solve it. Or in other words, it says that there does not exist any algorithm to solve that particular problem which runs in less than some constant times n. Is this point okay? Running time of that particular algorithm is at least constant times n, right? And here's the thing, that if I say that uh, Tn is another definition, I should say. Tn is both big O of Fn and Pn is both omega of Fn. Right. What does this mean? That to solve this algorithm runs in for example, let's say this Fn is n. Take Fn to be n. So it says that your algorithm is taking at least some constant times n many operations, and at most some constant times n many operations. But these constants are different. Let's say for some n and for some n for all n greater than n naught, and these constants should be different constants. See once, right? And we have a specific notation for this. We say in this case we say this is theta of f. Theta notation means both bounded above and below. Right? It's this analysis is kind of tight analysis. Okay. Any questions? Uh, what is theta notation? Uh, Theta notation is this. So if I write this definition, it's something like Tn, I'll say theta of Fn if say if and only if there exist uh, positive constants. Same as big O, it's a combination of big O and big omega. Theta is both big O and big omega. Positive constants C1, C2, and N naught such that C1 less sorry, C1 Fn is equal to Tn is equal to C2 for all n greater equal to n. Right? This is the definition. Okay. Can you give an example of? Yes, I can. The same thing. Tn is right. So we can show that Tn is in that big O of n to the power k. Tn is not big O of n to the power k minus 1, but Tn is big O of n to the power k. And also Tn is big omega of n to the power k. So I can say this Tn is theta of n to the power k. So I hope this is clear now. So I'll stop, make graph of this. Yes. So somewhere you have this Tn and you have this might be C2 Fn and somewhere your this is your um, not of this term. It should be something increasing. Maybe this is your P1 times Fn. Right? So beyond certain point, let's say for beyond this n naught, if you think anything, any value of n more than this, see Tn is less, Tn is greater than C times Fn, C1 times Fn, but Tn is less than C2 times Fn. Okay. Okay, fine. So I hope this is understood well. Uh, One thing is, have you done this in your programming course? Have you done the other sorting algorithms like selection sort and bubble sort? Okay, okay. So these are not done. So in in the next tutorial class, so I'll ask the TA to do the selection sort and bubble sort, those two things. Okay. So he'll not go in much details, but most likely he'll do this type of pseudo. He'll write this type of pseudocode in this term, and maybe some dry run he'll do so that you understand this process, right? And in the lab class, uh, you are supposed to, what is a TA means teaching assistant. He will be assisting this course and he will be taking the tutorial class and the lab classes. Right? I'll introduce you to him. Okay. And in the lab session for the first class, he, he will do the coding in C so that he'll also give you the basics of C language. I mean, since you have done Python, it will not be a big deal. Just few syntax you have to follow. That's it, right? Uh, one particular coding, this maybe this insertion sort or maybe the selection sort, he will do, and he'll do it for you. And rest of the two sorting algorithms, you have to do the coding in the lab class. Okay. Okay, fine. So I think I should stop now. Okay. Okay. Thank you, everyone.